Hello everyone, I welcome you all to the course Unmanned Air Vehicle Design, and in today's lecture we're going to see about vertical tail design. Vertical tail design is the third lifting surface in a conventional aircraft. It is the vertical tail, which is sometimes referred as vertical stabilizer or fin. From side angle, this vertical tail looks like this, which is having a rudder. The vertical tail tends to have two primary functions. First one, directional stability, and second one, directional trim. The vertical tail is a major contributor in maintaining directional control, which is the primary function of the rudder. Most of the aircrafts, when they are in flight, this vertical tail has a rudder here, which controls the movement left and right. It can go in this direction left, it can move in this direction right. When it is going in straight level flight, it can change its direction left, right using rudder. The following parameters must be determined in vertical tail design. First one, planform area, that is vertical planform, tail arm length, airfoil section. Generally, we go with symmetric airfoil. Then we have aspect ratio, taper ratio, tip chord, root chord, mean aerodynamic center, span, sweep angle, dihedral angle, incidence, and vertical tail location. This figure shows the vertical tail parameters. This is mean aerodynamic center of the vertical tail, which is here. This is CVT. This is span of the vertical tail. This is aerodynamic center of the vertical tail. This is the sweep angle. This is CVR. Root. This is root. This is tip. This part is root, denoted by CVR. This part is tip, CVT. In order to maintain the directional stability, the only location for vertical tail is aft of the aircraft CG. In many aircrafts, we have seen tails, for example. This is a CG. This is called aft tail configuration. This is CG and having a canard here. This is the front tail. We generally denote it as canard, and this is aft tail configuration. There are three possible candidates. First one, aft of the fuselage, wingtips, and booms. If a single aft horizontal tail has been selected, two places for the vertical tail is on the top bottom of rear fuselage, and the vertical tail cannot be placed in front of the fuselage. Right. This is the top and bottom. If we see from the side, either it will be at the top or it will be at the bottom. Since it makes the aircraft directionally unstable. If we place it ahead here, vertically, this is horizontal tail, right? This is also horizontal tail. Here it is vertical tail it is. This is horizontal tail. We cannot place it here as it will. We cannot place a vertical tail here as it makes the aircraft directionally unstable. It will create destabilizing contribution. In early stage of the vertical tail design, where other aircraft components have not been designed, the vertical tail moment arm is selected to be equal to the horizontal tail moment arm. Generally, the length we denote it as arm length. It is L. If it is vertical, it will be LV. If it is horizontal, it will be LH. This assumption means that the vertical tail is located at the same distance to the wing as the horizontal tail. The assumption will be modified in the later design stage when other aircraft components are designed and the aircraft directional and lateral stability, control and trim are analyzed. Once we are done with these parameters, this is X, Y, Z. Right, so this will have positive P, positive Q and positive R. P, Q, R, which represents rolling, pitching and yawing, directional. Right, and here it will have in x-axis it will be X, Y and Z. This will have velocity component of U, velocity component of V and velocity component of W. Right. So once we know the sum of forces and sum of moments equal to 0 at equilibrium, sum of forces and sum of moments is 0 at equilibrium, then we can control the stability. This longitudinal axis is completely, this one completely governs the longitudinal stability. In Y direction, which is wingtip to wingtip, is lateral stability, and this vertical line which is perpendicular to X and Y is directional stability. The vertical tail area must be large enough to satisfy directional stability, control and trim requirements. Trim is bringing aircraft back to equilibrium position after it is disturbed, and it is a point where we have steady level flight condition, that is lift equals to weight and thrust equals to drag. Two most effective parameters in directional stability are Cn beta and Cnr. The value of Cn beta for a statically directional stable aircraft is positive. A higher value of Cn beta implies a more directionally statically stable aircraft. If the aircraft is in the manufacturing stage and the initial vertical tail design may not be changed, one solution to increase the vertical tail area is to employ a dorsal fin. This looks like this. We'll have a fin here. This will be the dorsal fin. A dorsal fin is generally a flat plate. It's not an airfoil section which is installed in front of the original vertical tail with a greater sweep angle. The other benefit of dorsal fin is to reduce the minimum control speed during takeoff operation. In addition, it provides a hidden antenna feature that allows the antennas to be located under the fin for further drag reduction. Another approach to solve the small vertical tail area problem is to employ ventral fin. The vertical tail incidence is defined as the angle between the vertical tail chord line and aircraft exit plane. Exit plane, when we look at the aircraft from the top view, it looks like an exit plane where we get to see the aircraft with wing combination. The vertical tail is responsible for the generation of vertical tail lift coefficient. One of the basic aircraft design objectives is the symmetricity about the exit plane. Hence, if the engines, wing, horizontal tail and fuselage are designed to be symmetric about exit plane, the vertical tail is not required to produce any lift to maintain directional trim in normal flight. For this reason, the vertical tail incidence must be initially 0. The vertical tail design requirements are as follows. Directional trim. If it is disturbed due to the gust loads during the flight, if the direction is affected due to the gust loads, this vertical tail plays a crucial role to bring it back to equilibrium position. Then directional control, directional stability, manufacturability, handling qualities, stealth nature, which is only for specific military unmanned air vehicles, operational requirements, airworthiness, cost, competitiveness and height limit. These are the some areas which we should be considering during vertical tail design requirements. First, we need to select a vertical tail configuration, whether it's a conventional tail, twin tail, vertical tail at swept wing tip or V-tail. Depending upon the configuration and as per the requirement, we'll select the vertical tail, and after the selection of the configuration is done, we'll find the vertical tail volume coefficient, or we'll choose it from the existing historical data. After determining the tail volume coefficient, we determine the vertical tail moment arm length, the distance, the length of the vertical tail moment arm, and then calculate vertical tail planform area, select vertical tail airfoil section. Most of the times it will be symmetric airfoil because it tends to maintain stability on either sides, on the left and right hand side of the aircraft. Then we select the vertical tail aspect ratio for its agile nature. Then we select vertical tail taper ratio. Then determine the vertical tail incidence angle, that is IV. Then determine the vertical tail sweep angle. Then determine the vertical tail dihedral angle. After these 10 steps are done, then the 11th one is calculate vertical tail span, root chord and tip chord and mean aerodynamic chord. Then the tail is tested for spin recovery. After spin recovery testing phase is done, adjust the location of the vertical tail relative to horizontal tail by changing the tail movement arm to satisfy the spin recovery requirements. We analyze the directional trim, then after that directional stability is analyzed, then it is modified to meet design requirements and optimize the vertical tail. Once all stages 1 to 17 are done, we draw the final design with dimensions. The vertical tail design is an iterative process. When the other aircraft components such as fuselage and wing are designed, the aircraft dynamic, longitudinal, directional stability needs to be analyzed, and based on the outcome, the tail design may need some adjustments. The other vertical tail parameters which we have to consider in the tail design process are vertical tail parameters such as airfoil section, aspect ratio, taper ratio, sweep angle, and dihedral angle are governed by similar fundamentals as those of the horizontal tail. The final values for these vertical tail parameters are determined when the design requirements such as directional stability, efficiency, cost, and safety are examined. Purpose of the vertical tail: it provides directional stability. It resists the unwanted yaw disturbances during flight. The second one is yaw control, which enables the controlled turns through rudder deflection. Spin recovery: it assists in recovering from spins or high angle of attack situations. Crosswind handling: it provides yaw authority during takeoff and landing in crosswinds. Engine out conditions: for twins or more than that, it offsets a symmetrical thrust. The major components which contribute in vertical tail design: first one, fin. It's a vertical stabilizer. It is a fixed surface that provides stability. The second component is the rudder, which is a movable control surface hinged to the fin for yaw control. This is rudder. It will deflect to left and right such that we can control the direction. Dorsal or ventral fins are optionals, which are added to improve effectiveness and control in certain configurations. The design parameters which we consider during vertical tail: the first one, area of vertical tail. Based on empirical ratios and wind tunnel data, it depends on aircraft length and configuration, mass distribution, engine position, for example, whether it is fuselage mounted engines, which increase yaw, moment in failure, mission requirements, which is maneuverability versus stability. Aspect ratio and sweep: higher aspect ratios give better aerodynamic efficiency but may reduce structural strength. Swept fins delay stall and improve high speed performance. Rudder sizing: it provides sufficient yaw moment for engine out of control, that is in case it is multi-engine aircraft, crosswind landings, and spin recovery. Rudder deflection is limited by structural limits, pilot effort, stability and control requirements. The trends and innovations: There are V tails, which are also called as rudder waiters, which combines vertical and horizontal tails. Example, which we can see in Beechcraft Bonanza. The vertical and horizontal tails are combined in this case. Twin vertical fins, which improve stealth nature. It reduces the height of the aircraft. For example, F-22 and F-18. Active controls, we have fly-by-wire systems which allow reduced size with enhanced stability augmentation. Composite structures for weight reduction and improved fatigue life. Conclusion of this lecture: the vertical tail, also known as the vertical stabilizer or fin, plays a vital role in ensuring the directional stability and trim of an aircraft. It acts as the third lifting surface in a conventional configuration and supports the rudder in maintaining directional control. Its effective design is essential for achieving stable and controllable yaw motion, especially during asymmetric flight conditions and crosswind operations. These are the references used for this lecture. Thank you. We'll meet in the next lecture.